Yes, so hello, I'm Kenneth again.
Hello, Kenneth.
Hi,
Hi,
David.
Ken.
Hi, guys. W6KWF, and that's my website right there. And I am the project coordinator for this club, and so in light of that, I'm giving this talk to you guys on the background of batteries as far as the actual chemistry that goes on, what different sorts of lead-acid batteries there are, the advantages and disadvantages of lead-acid batteries, and then we'll go into actually charging a lead-acid battery and kind of how you would design your own lead-acid battery charger so that if you wanted to build your own battery charger, you could do it. And then, because we're an awesome club, if you build a lead-acid battery charger and show it to me, you get as a prize a free sealed lead-acid battery from the wonderful Environmental Health and Safety Department, slightly used, but still perfectly good. So if you want, so that's the reason why you should be paying attention. Yes, Eli.
Are you relying on us for applause and laughter, or are you going to dub that in later?
Oh, there's going to be so much post-editing you won't even recognize this. Yeah. So, lead-acid batteries. In amateur radio specifically, and in many other applications, lead-acid batteries are a very prevalent chemistry. Specifically in amateur radio, it's used for almost all of our equipment. Almost none of our equipment has a 112 volt, 120 volt jack on the back of it, but instead has a 12 volt jack so that you can take a lead-acid battery and directly hook it up to it. For example, this was our operating position at Field Day 2 years ago. We were running a digital station, and so we had several deep cycle flooded marine batteries, which were powering a laptop that had 12 volt in on it, a sound card, a radio, and then we, for 24 hours, were able to operate completely off the grid using batteries. So why are all of these applications using lead-acid batteries and not other chemistries? Namely, lead-acid batteries are the oldest rechargeable chemistry that exists. Gaston Plante discovered the lead-acid battery back in 1859, and at that point they had only had non-rechargeable batteries, and so this was actually a fairly large breakthrough at that point. Originally, this was 1859 was actually before they discovered the electric generator. And so if you're studying for your amateur radio test, or if you're reading any literature on batteries, they always spend this distractingly long amount of time discussing primary versus secondary batteries. Primary batteries being the non-rechargeable ones, and the secondary batteries being rechargeable batteries. It's likely that didn't make much sense to you. The reason why that is called, they make the distinction between primary and secondary, is because to originally form a lead-acid battery, which I'll talk to you about in the chemistry section, you had to pass current through it several times. Before they had discovered the electric generator, they literally did this by the fact that they took copper and zinc plates, polished them, and put them together to make a primary battery, and then use this primary battery to recharge, build, and then recharge the secondary batteries. And so it was literally a primary was the first, it was your energy source, to the secondary was how you stored it. Since recharging these batteries is quite a bit easier than having to physically remove and reinstall a new battery stack in each application that you're using these batteries in, which back then was everything, right? Well, everything they use electricity for. So railroad systems, lights, telegraph, telephone, almost everything, because it was actually a tremendous number of, out on telegraph lines, they would have buried in the ground every few miles this big lead-acid battery bank they would use as the amplifiers for the telegraph system. And that's because that was the only rechargeable system they had, and then when the lead-acid batteries died, they'd have to recharge them. Once the electric generator was discovered in the late 1800s, lead-acid batteries got tremendously cheaper. Lead is cheap, right? The Romans used it for plumbing. They actually made pipes out of it and ran it through one of the many downfalls to the Roman Empire.
Is it like the lead in their piping system equivalent today of putting uranium in our drinking water almost or something? Because that's basically what made Roman insane.
Oh, there was several problems with the Roman Empire.
That's true.
The fact that they used lead for their plumbing was probably one of the smaller ones.
It's like that lead eventually caused them to go insane from drinking water.
Actually, the lead in their drinking water was actually fairly negligible compared to the fact that much of their drinking-ware and silverware were also lead. Acidic alcohols such as wine are quite a bit more effective at leaching heavy metals like lead out of surfaces than drinking water is.
So, but they did die of lead, or they did go insane from lead poisoning, right?
Sure. We have little medical history from the time. Lead acid batteries are very rugged compared to lithium ions, which have the propensity to, when you abuse a lithium ion battery, it'll catch on fire and very vigorously combust and or explode. Lead acid battery is kind of the worst that happens to most lead acid battery failures. Kind of the worst that happens is that it stops working. Maybe it vents a little bit of sulfuric acid, but if it's in a correctly installed area, that doesn't mean anything. And it also has a very high power density. This is why lead acid batteries are used to start your car. Starting your car is a very short, very high power event, right? When you turn the switch on your car for 2 seconds, you need to have enough power to turn the engine over several times and get it to start spinning at several thousand RPM. If you've ever tried to actually physically manually turn an engine over, you'll realize it's actually a royal pain in the ass. So the fact that it has a high power density is very attractive. The cons to it is the fact that lead is bad, right? Bad for the environment, bad for you. It kills babies. And it's really freaking heavy, right? Lead acid batteries are very, very heavy. For example, here's a 12 amp hour lead acid battery, and as you realize as I pass this around, it's really heavy because it literally is large plates of lead. Conversely, most people don't appreciate how effective lead acid recycling programs are. Is from your typical properly disposed lead acid battery, the recovery rate of all materials in the lead acid battery is about 98%. And the 2% that's lost is actually primarily the paper fibers used as the separator between the plates in them, because you put a bunch of paper fibers in acid for a decade, they're going to pretty severely degrade. So that's actually the primary waste product of the lead acid batteries recycling system. So as far as like it being bad in the same way that lithium ion is, that really isn't the case. Lithium ion is of course also getting quite a bit better as we move along, so recycling is awesome. Lead acid is also a very low energy density. The difference between high power density and low energy density is that while you can start your car for very quickly by having just turning the switch and then boom, over 2 seconds your car is started, at the same time, you can't drive very far on this lead acid battery, right? This is why you can start your car right away, but at the same time, if you leave your headlights on overnight, your battery is dead because there isn't much power there. So actually, a significant fraction of your car's battery is used in starting the car. So low energy density, high power density. As I mentioned, amateur radio operators use lead acid batteries primarily as a backup system. On the right is my buddy Phil, carrying one of his lead acid batteries around on field day. We were up on the top of a hill, and for 24 hours, we ran completely off the grid and scored a tremendous number of points and set a new world record in our category. On the left is the back porch of my apartment. I have, just hanging out on my back porch, 4 6-volt batteries, which I have wired up as a 12-volt bank of batteries. And it sits there with a trickle charger all the time. And so that if there was a major event in San Luis Obispo, I have 400 amp hours of 12 volts at my disposal to keep my radios running as we help reestablish infrastructure and communications in San Luis Obispo County. It also keeps laptops and cell phones charged, which is my primary motivation because forget the rest of you. When I say it's a 12-volt battery, I don't actually mean it's 12 volts. Much in the same way as my last talk, I said that a diode has a forward drop of 0.7 volts. A diode doesn't have a specific voltage drop to it. The actual electrochemistry going on in a lead-acid battery cell produces a 2.1 volt potential between the positive and negative plate. So when I say 12, we're really actually rounding from 12.6 because we like to be creative with how we round. But there's no reason why batteries have to be 12.6 volts. You can have batteries that are any multiple of 2.1 volts. Amateur radio equipment has all been designed to run on 12.6 volts, but if you actually read the manuals, they'll actually say something like 13.8, which is essentially 12.6, but just at a different state of charge. And so if you read these manuals, you're wondering where the heck is 13.8 or 13.5 coming from. That's coming from the fact that a lead-acid battery on a float charger is usually floated at 13.8 volts. And I'll talk about that when we design our lead-acid battery chargers. A whole bunch of other voltages. You can get individual lead-acid battery cells that are the size of a D battery. These are used usually in telecom, UPS systems, and portable power packs for bench equipment. So a bunch of old HP multimeters, spectrum analyzers, pretty much any bench equipment that had internal batteries in them. Many of them were either these D-cell lead-acid batteries or nickel cadmium, which is a different chemistry. 6 volts, 8 volts, pretty much anything you want. When we describe a battery, there's a couple different specifications we use. The battery voltage is kind of the most obvious one. I passed around a 12-volt battery. This is also a 12-volt battery. This is an absolutely adorable 12-volt battery. And all that means is that it has 6 2-volt, 2.1 volt cells in it. So any 12-volt battery is a 12-volt battery. That being said, not every 12-volt battery is made the same. This battery and this battery are obviously not the same, seeing as how one of them is moderately sized and one of them is adorable. And that's where the amp-hour rating comes in. So that is a 12 amp-hour battery over there. This is a 7 amp-hour battery here. What that means is that if you were to hook this up to some sort of system that needed to draw 1 amp at 12 volts, this battery would be able to supply that 1 amp for 7 hours. This is kind of an academic measurement because 1 amp for 7 hours versus 7 amps for 1 hour are actually two very different things. On the load side, it's the same, but the actual chemistry that goes on, a 7 amp hour battery is not going to deliver 7 amps for 1 hour. And how these manufacturers specify their battery capacities are much the same way that hard drive manufacturers specify their capacities. They come up with these creative numbers and creative math that kind of make their batteries look really awesome. As a frame of reference, this is a 1.2 amp hour battery. So you could not run much on this, but it would run it quite adorably. So the amp hour rating, like I showed you before, those batteries on the left are each 200 amp hours, but they're only 6 volts each. So when I put 2 of them in series, I have 12 volts, but it's still only 200 amp hours. The reason this is a 400 amp hour bank is because I have 2 of them in series and then 2 pairs in parallel, right? So in series, the amp hours have to be equivalent. In parallel, the amp hours add. Another frame of reference, your standard alkaline AA battery is 1.5 or 2.5 amp hours, but it's only 1.5 volts. So when you compare 2 batteries, amp hour to amp hour, you need to make sure that the voltages also match, or else you might be comparing 2 very different levels of power, right? You can take 100 9-volt batteries, hook them in series, and you have 900 volts, but you still only have 200 milliamp hours. So it'll hurt, but not for very long, for a number of reasons. The physical configuration of the lattice battery is about the third specification is starting versus deep cycle. When I say that a battery is a starting battery versus it is a deep cycle battery, we're talking about exactly how the plates are physically designed and what loads that battery is designed for. A starting battery is a battery that's designed to very quickly start something like a generator, like your car, like a locomotive, pretty much any big thing that needs a pulse of energy, and then it is designed to then immediately be recharged back up to its fully charged voltage and sit there until the next time you need to start your car. A deep cycle battery is a battery that instead of it being designed for one very high power burst, is instead designed for a longer extended release of power, and is designed to, instead of it just being one usage and then recharged, be actually deeply discharged significantly before eventually being recharged. Uninterruptible power supplies would use deep cycle batteries. Marine batteries are about the most accessible amateur radio batteries. So if your boat has an electric motor in it, you would use a marine battery. Backup systems for data centers, telecom equipment, that's all going to be deep cycle. Because if the power goes out and you want to keep your computer up, being able to keep it up for 5 seconds as it sits there and chews through all your battery life of a starting battery isn't very useful. A starting battery can't hold anywhere near as much energy as a deep cycle battery, but a starting battery can deliver much more power. Right? If you're running a backup system, you want low power over a long time, not high power for a few seconds. Finally, the last one is how the acid is actually held within the cell. The three major ones are flooded cells, sealed gel cells, and absorbent glass mat cells. Flooded cells are literally big plastic boxes with little caps on the top of them that you can open them up and you can look inside of them, and you can see floating about 2 inches below you a giant pool of sulfuric acid. If you wanted to pour that sulfuric acid out, you could. This is advantageous because it means that you actually have physical access to the sulfuric acid inside these batteries, which is useful for a number of reasons. It'll let you maintain the batteries, because after time, the water inside this battery is going to dry off, and you're going to need to put more water back into it. It also lets you check how well charged it is. As a battery discharges, the voltage will change a little bit, but a better indication of it is actually the chemistry of this acid inside of the cell. And so when you're checking the state of charge of a large flooded battery bank like this, you would actually take a hydrometer and check the density of this acid to see how much sulfuric acid versus just distilled water is there. When you maintain these batteries, it is critical that you use distilled water and not tap water. That is because you really want to make sure that you're only adding water to these batteries, because if you add heavy metals to it, hard water, calcium, magnesium, any of these other minerals that you find in normal tap water will very quickly deeply degrade these lead-acid batteries. Lead-acid batteries are very much depending on the surface of these plates and them being able to react chemically with the acid, and if you put a layer of calcium on them, your batteries will no longer do anything. Conversely, these are sealed gel cells here. We like them because they're sealed, because we can throw them around like this and we don't have to worry about spilling sulfuric acid on ourselves. I have regularly spilled sulfuric acid myself working on batteries. It's not fun. If you don't catch it right away, it's painful. It's messy. So in applications where you're going to be moving this stuff around a lot, where it's going to see lots of rotation, gel cells are attractive. Motorcycle batteries are one of the, used to be flooded. You'll see most motorcycle batteries are now sealed, because they finally have gotten sealed batteries to a high enough quality that they don't have to use flooded cells for motorcycles anymore. And motorcycles is, again, one of those things where it's going to see lots of rotation, lots of vibration, lots of movement, that for a flooded cell is not ideal. Absorbent glass mat batteries take that argument one step further, and instead of it being a sealed gel, like in here, the electrolyte, which is the acid in the water, is actually soaked into a fiberglass mat, which is then physically compressed between the two plates of the battery. And I will show you a low-resolution picture of one of those. So, various battery sizes. These are the D cells I mentioned, and they are absorbent glass mat cells. So, if you see that right there, that white stuff, I took the foil, as I took the foil off of it that said silent on it, off of this battery, and that white stuff is mostly the fiberglass with, on the top of it, an edge of sulfate crystals. These batteries came out of 48-volt telecom backup systems, because your telephone line is a 48-volt system, and you expect your telephone to still work when all the power goes down. That's done by these battery banks here. These would be mounted in this big flat sheet about this big. That would be 24 of these cells in series, and will be able to keep your telephone up for quite a bit longer. These batteries are also about 3 decades old, and I was playing around with trying to rehydrate them because they were well beyond completely dried out, which was essentially a waste of time. Because once a battery gets dried out like this, it's usually just dead. So maintain your batteries. This is my personal battery bank. You'll see that I have grossly undersized wire routed between them because this is designed to be a long-term backup solution, right? If I was trying to actually pull anywhere near the actual rated amperage of these batteries out of them, I would need much heavier cable around it. But since I'm planning on using this to run my cell phone, my radio, my battery charger for possibly a week or more, I use light wire between them. And then you can see the 3 caps, which indicates that these are 6-volt cells. And so every quarter or so, I have to open up those caps, check the fluid level in them, and I have a bottle of distilled water. I refill them up to the market point on it. So those are deep cycle batteries. This set originally came out of a scissor lift, because I was helping a guy service a scissor lift used to do scaffolding work and stuff, indoors. And they replaced the battery bank, and we're looking at some way to get rid of it, and so I graciously volunteered to acquire his e-waste for him. Going even larger, in diesel electric locomotives, they use a 64-volt system, which is actually spread across 8 8-volt batteries. So that is me on the right there. On the left, on a pallet, you will see 4 8-volt batteries. Each one of these batteries is literally the size of a suitcase and weighs about 300 to 400 pounds. These are starting batteries, and so even though they're only rated for about 500 amp hours, they can deliver that 500 amp hours very, very quickly, which makes sense considering that in a locomotive, you're going to start it in only a few seconds, and then you're not going to need to start the engine again for possibly months. This is me volunteering at the Western Pacific Railway Museum, if you're curious why I happen to be working with locomotive batteries. This is another shot of the locomotive batteries on the left here, and on the right, this is what happens when you don't maintain your batteries. What happened was we didn't keep all of our batteries well charged, and as I will go through on the chemistry section, when you don't keep batteries well charged, the sulfuric acid will actually turn into water, pure water. So if you've got a fully discharged battery and not a strong will to live, you could actually pour the distilled water out and drink it. It would be a bad idea, and you're never going to actually get a battery fully discharged, so don't do that.
I don't think it's a good idea to drink sulfuric acid.
Yeah. Drinking sulfuric acid is bad, drinking water is okay. That's the dilemma. And so what happened was, since this is up on the Feather Canyon on Highway 70, the winters are tremendously colder than us Californians are accustomed to, and since at that point it was no longer sulfuric acid but was just water, since sulfuric acid acts as an antifreeze, the water froze, expanded, cracked each individual cells, and blew the battery apart. which didn't make a tremendous mess until then all the ice melted, and we then had sulfuric acid all over our battery. But luckily it was very dilute sulfuric acid because we don't make inner batteries. It's kind of interesting because you can see the individual plates inside of this battery. So we're looking at a cell that's about the size of a milk crate here, and each individual pair here, the two that are closer to each other, is one plate, and then there's paper wrapped around the other plate, which is indicated by these white crystals on the top here. The white crystals are sulfate crystals, which again is indicative of poor maintenance. Much like these batteries are leftovers from environmental health and safety, these batteries are leftovers from Class 1 railroads because we're a museum and volunteer organizations often have a lot of money. So now let's talk about the actual chemical reaction that is going on inside lead-acid batteries. After I get a drink of water, and anyone who has questions, ask me a question. No questions.
Field day 2 years
And
ago.
pizza, let's do a pizza break.
How do you distill your water?
I use a retort.
What's your
A retort is that little glass sphere with a long neck out the side of it, which you almost will pretty much only see in video games as one of your alchemy equipment.
Oh, I remember that.
Yeah, is originally how I made distilled water was I had a retort, a alcohol burner, and then I had a full coil condenser. Unfortunately, I cracked the coil dispenser, the coil condenser, and so now I try and condense the water just on the neck of the retort, which is tremendously inefficient. And now that I have this battery bank, it now makes sense. I just go to the grocery store and buy it for like 98 cents. Right? It doesn't make any sense to buy water to drink it, but when you're buying distilled water to be used in chemistry like this, 98 cents is not that terrible. So honestly, just buy it. Because trying to cook your own distilled water with a retort, you want that one? There you go. Sorry. Trying to cook your own distilled water in July in the Bay Area is not a fun experience.
It's hot.
It's very hot. You're boiling water. Right? So yeah. So just,
Then just use a solar cooker for it?
you could. If you had that much prior knowledge of your need for distilled water, you could just go walk to the grocery store and buy a gallon and get back before you've gotten a pint or ounce of water out of it. All right, so let's talk about lead-acid batteries. So now I'm going to, in comic form, do a dramatic reenactment of a lead-acid battery cell for you. So here is our large plastic box. And inside of it we have two metal plates. One metal plate, two metal plates. Originally, how this battery was formed was that the Gustave Plante, whatever his name was, would take two pure pieces of lead and then would pass current through it and grow it into the appropriate oxides of lead that you need. There's better ways to do it now, but that was how you would originally do it. You can actually reproduce this yourself by taking a couple little pieces of lead, pounding them into two sheets, put them in some water, and you can get yourself an absolutely pathetic battery. Because the power of this battery is dependent upon the surface area of the two plates. And two pieces of foil compared to an actual lead-acid battery has relatively little area. We're going to call this the negative plate, and this is the positive plate. So these wires would then run off to whatever you're driving with this battery, be it a car, be it your radio, be it your iPod, be it Shocking Nolan, does we do that? And in a fully charged state, we have sulfuric acid hanging around here, we have a pure lead plate, and a pure lead oxide plate. So the positive plate is all lead oxide, PbO2, and then the negative plate is all Pb, or just pure elemental lead. Then inside of this water solution in here, we then have dissociated H2SO4 sulfuric acid, and so it's really sulfate ions floating around and hydrogen ions floating around, thus it's an acid. When you discharge a battery, that's you pulling energy out of it. A battery is discharged by the fact that you have electrons forced out of the negative side and forced back in through the positive side. Damn you, Benjamin Franklin, for guessing wrong on which way the charging electron was, and so that we have to constantly remind ourselves that current flows one way and electrons flow the other way. So, on the surface of these plates, right here and right here, there is an electrochemical reaction between the lead oxide, the lead, and the sulfuric acid that causes this electrical potential to appear. When this was originally discovered with copper and zinc, which was the first primary battery discovered, they were very much confused, and since they lacked voltmeters, actually built tremendously large stacks of this, and through some painful experience, actually figured out what the hell is going on. On this surface, we're actually going to exchange sulfate ions with lead. We're going to exchange sulfite ions with electrons in the lead, and exchange sulfate ions with oxygen in the lead oxide. So as you see on the negative plate, we're going to take pure elemental lead. We're going to take sulfate from the acid and bind the sulfate to the lead, have a free hydrogen ion, and have electrons emitted up through the wire. Conversely, on the positive side, the electrons will flow in, and those electrons, plus the aqueous hydrogen ions that are in the solution because this is an acid, plus more sulfate ions, will force the oxygens off of the lead plate, create lead sulfate, and create water. And so when you're discharging the battery, you are literally converting sulfuric acid into water by pulling the oxygen out of the plates and then rebinding the hydrogen ions, instead of being in a free acidic form, into water. Cool. So in the fully discharged state, we now have two plates that are both entirely, and when I say entirely, I really just mean the surface, right? Like it's not like it actually migrates in the middle of it, of lead sulfate, so PbSO4. PbSO4, and then in the middle, we now just have water. This is why we like lead-acid batteries, from the fact that we can check the state of charge very easily, because water has a pronounced density difference from sulfuric acid. So if you take your hydrometer, which has in it a little floating bubble thing, and you see how dense this liquid is compared to distilled water and sulfuric acid, you can figure out what percentage of the sulfuric acid has converted into water. Recharging the battery is then the exact opposite reaction. We, on the plates, on the external connections, force electrons back into the negative plate, force electrons back out of the positive plate, and then that causes the lead sulfate on both plates to disassociate from the lead plates themselves and travel back into the electrolyte and create sulfuric acid, right? So we charge, we discharge. Ideally, this is a fully conservative process that we can do forever. Unfortunately, the real world is inconvenient and doesn't support such things as that. A pure plate of lead like this has very little surface area. A plate of lead the size of a postage card has the surface area of a postage card. we want more surface area than that because we're humans and we like bigger and better things and smaller and more adorable packages. And so how these plates are actually physically constructed is that it is a plate of lead with a bunch of holes or voids in it in which lead paste is placed. And so instead of it just being a plate, it's actually more of a sponge. And so you would have in it just little chunks of lead powder that has been properly chemically treated. And so much as a crumpled piece of paper has quite a bit more surface area than this, a lead plate that has in it all sorts of a lead paste like this has a lot of surface area. Paste doesn't have a tendency to want to stay in one place. As we all learned as children, paste inevitably ends up on the floor. In the same way, every single time that you cycle this and all this paste chemically converts into lead sulfate and then back, a little bit of it is going to shed off to the bottom. Depending on exactly what sort of battery you have, you will design this reservoir at the bottom to support various levels of shedding.
So are you saying that as the paste wears out, our plate is going to break apart?
Yes. In starting batteries, you won't need to concern yourself with this over too much because you're only using a little bit of the paste because you're just using it for a couple cycles at a time. Conversely, in a deep cycle battery, you're going to be converting almost all of this paste one way and the other, and so you're going to see quite a bit more shedding the deeper you discharge it. This is true for practically all battery chemistries. The deeper you discharge it, the more damage you will do to it. Memory effects in batteries is a myth. It always has been. Like with nickel cadmium, it was debatable. Ever since then, memory effects have always been false. And so the more often you can recharge your device's batteries and the higher and the less deep you can keep them from being discharged, the longer they'll last. Right? The person who every time they use their laptop deliberately fully discharges the battery before charging it, their laptop pack is going to die years before my laptop pack dies because I very deliberately, whenever I have a chance, run it off of the wall because I don't want to discharge it all the way and then recharge it again. Right? The only advantage you get to fully discharging the battery in your cell phone and recharging again is a little percentage sign on top of it is more accurate. Conversely, if you just always charge your phone when you have the chance, you don't even need to really worry about what the percentage sign says. So don't discharge your batteries.
So is that also true for like if your battery is fully charged in your laptop and you leave it plugged in, is that bad for it, or is that meant to?
Technically, it's bad storing batteries in high temperature environments. The chances of you doing more damage with your laptop in a properly cooled configuration with the battery in it versus leaving the battery out of it, losing the battery, accidentally shorting the battery to itself with a lead pencil, accidentally letting the battery completely discharge, the inconvenience of no longer having a battery in your laptop. I mean, there is some argument to the fact that when you have a laptop battery heated like that in a laptop, it's bad for it. But again, maintaining the full state of charge on it is, and no one's going to have some comment on that.
Lithium batteries, they all have battery management circuits, so when you leave it plugged in, it's not actually charging anymore. When it says it's done, it lets it drop to like 95% and charges back up and lets it drop.
So again, fully charge your devices because they're smarter than you are.
Yeah.
So is it a good idea when you get a new computer that's fully charged to leave it unplugged when you first start to leave the drains battery?
The only advantage to that is the only reason you'd ever want to do that is so that the little counter on the side that says you have 2 hours left would only be off by an order of magnitude instead of 2 orders of magnitude. Because those things are still baloney because they're never right. Right? And so the only way that it can calibrate itself is by you fully discharging it. But the amount of power that your laptop is consuming based on what you're doing is an order of magnitude more than the standby power consumption of your laptop.
lithium batteries, there's lithium polymer, lithium ion chemistry is used in consumer devices. They tend to work best at about body temperature, which is conveniently what your pocket where your cell phone is in the back of your laptop.
Exactly. So if you guys ever have problems with devices like that in cold regions, suddenly not working, literally just warm up, right? The old trick when you had the Game Boy, you would pull the AA batteries out and you would run them between your hands and get a couple more minutes of gameplay out of it. Exactly the same thing. With lead acid, you know, in theory, you can do the same thing. I think they have a negative temperature coefficient, so every degree Celsius of a lead acid battery goes up. The voltage, the standing voltage of it goes down by 20 millivolts. That sounds. Anyways, so there is an ideal temperature for every chemistry. It's rarely at room temperature. It's almost never hotter than hot. So keep your batteries cool, keep them charged, and they'll be happier. Where was I before I went on that rant about memory effects? Yes, so the charging, discharging cycle. All this paste means we have more surface area, but at the same time, now our plates aren't actually plates of lead. They're now these kind of precariously held together buckets of paste, which is why batteries after a while wear out and need to get replaced, and why ideally you should discharge your batteries fewer times. If any of you have experienced a problem where if you leave your headlights on your car on for a week and a half and they get totally, your battery is completely dead, even if you recharge it, suddenly your battery is never really going to be quite the same. And you know, after you leave your headlights on a couple times, my girlfriend actually, one of my girlfriends at one point had this problem. She accidentally left the headlights on a few too many times, and then she couldn't keep her car charged for more than 2 days apart. Right? Because once you lose all of this paste and all the surface area, the battery capacity goes from 30 amp hours down to 1 amp hour or half an amp hour, and that doesn't start a car. The other problem with having a battery be deeply discharged and then left in a state of deep discharge is the fact that both of these plates are lead sulfate. Lead sulfate in the amorphous state, which is what it is when it's converted as its paste, is very electrochemically available, which is good because we want to be able to put power into it later and convert all this paste back into something that's not lead sulfate. Lead sulfate, if left in the lead sulfate state for a long time, has a tendency to crystallize. Lead sulfate actually has 4 separate levels of crystallization, which is master's level material science stuff, but primarily as lead sulfate is left to sit there for longer and longer times, these crystals, as it passes through these levels, energy levels of crystallization, the sulfate crystals become more and more and more difficult to electrically break apart again. So a battery that's been fully discharged and just sits there, all of this sulfate will solidify into a very unreactive crystal that you can't recharge again. Also, these crystals have the problem that when you have crystals growing on these plates that are separated by a piece of paper, the crystals will grow through the paper and short out the 2 plates. And so your 2 very carefully separated plates on your lead acid battery suddenly become 1 plate, and when you try and recharge it, you'll instead discover that you're merely heating up your battery and doing nothing for the actual recharging concept. Right, Nolan? Yes. Close enough? Good. Conversely, if you manage to get a battery that's in bad condition, particularly a flooded one, and you get it in just the right charge state so you can see these sulfate crystals grow and shrink, it's totally awesome because they make these great leaf patterns as they go from one plate to the other. And then if you're feeding it with a powerful enough charger, as soon as the 2 sulfate crystals meet together, they'll polarize. Safety lesson, guys, safety.
Polarized.
Like underneath water goes pop.
So it just explodes.
Pretty much, because these sulfate crystals are thinner than a human hair, and I'll put 10 amps through them. 10 amps through anything that's smaller than human hair, other than possibly carbon nanotubes, will go pop. Let's see, sulfate. Sulfate is bad. It physically distorts it. Crystals growing also tends to shove out more paste, and sulfate crystals, when they form, tend to collect on the bottom. Once this pile of paste and sulfate crystals and junk and dropped jewelry, gets up to the bottoms of plates, suddenly again you've shorted out the cell, and that cell is no longer any good. Trying to replace one cell in a 4-cell pack is really inconvenient. So at that point you would generally just say, this pack is dead, give me a new pack. But if one of your cells has died, the whole pack is generally in pretty bad condition. So that is the electrochemistry of the lead acid charging and discharging cycle. And that's why you can discharge this. Conversely, other battery chemistries such as alkaline, mercury, zinc, air, lithium, not lithium ion like 4-volt lithium, but the 3-volt lithium ion, not lithium ion, just lithium something. You can't recharge those because the products of the discharge reaction are not electrically available. And so while lead sulfate in its amorphous state is very electrically available, the salt products of a discharged alkaline battery are significantly less available, and what they do geometrically inside the battery is much less predictable. And that's why recharging an alkaline battery is bad, because you don't know exactly what it's going to do, and the tendency for it is to do bad things, because when light can do bad things, it'll take the chance. So you shouldn't. Safety. Safety glasses. And obviously when you're dealing with sulfuric acid, safety glasses, gloves, splash mask if you're really actually doing anything major with it. And then I also have saline eye wash solution on hand, and usually a heavy squirt bottle of some mild base solution. My personal preference is just baking soda. So I'll make a saturated baking soda solution. And there's been several times when I've gotten either sulfuric acid or sulfate crystals in my arms, and I'm looking at this and I'm like, this is starting to hurt. I can just take baking soda, wash it all off, and I've neutralized the acid. So, fun trick if you're ever working on this sort of stuff. Hey, so now let's talk about the voltage, the charge cycle from the electrical viewpoint as just a user of a lead acid battery. A fully charged lead acid battery that has been sitting fully charged for a moderate amount of time will, when you put a voltmeter on it, read 12.6 volts. Hey, 12.6 volts open circuit. When you have fully discharged the lead acid battery cell, it will drop the relatively small voltage of 1 volt per 6 cells down to 11.7. So the voltage of a battery pack is a moderately good indicator of charge state, but not a great one. That's why we like the fact that we can pull the electrolyte out of a flooded battery and actually play with it chemically. Under load, a fully discharged battery will be about 10.5 volts. Personally, in amateur radio operations, our cutoff point is usually 11.5 volts under load, because we'll usually have spare batteries that we can swap in, and the deeper you discharge it, the more damage you do. And so in a drill situation, there's no point in fully discharging your battery down to 10.5 volts under load, because it's a drill. And if the lesson learned is, oh, I need an extra battery, you've just learned a lesson from your drill. And that's why we do safety drills like this. The recharging cycle of a lead acid battery consists of 3 major stages: the constant current stage, the constant voltage stage, and then the floating stage. The constant voltage stage is the most intuitive. You take something slightly higher than the battery pack voltage, apply it to it, and you let energy go into the battery until eventually the battery is charged and says, hello, I'm charged. But they don't say that. Unfortunately, you can't just do that, because a fully discharged battery doesn't look like a resistor. It looks like a battery, which electrically has very, very low impedance. The actual pure resistance of a good battery is measured in milliohms. So if you just take 14 volts and apply it to a 11 volt battery pack, and that battery happens to have a 5 milliohm internal impedance, you just put 3 volts across 5 milliohms, it's going to draw, what is that, a little bit over 1,000 amps.
So we die if that happens?
The battery would be very unhappy. So you would probably, as part of the shrapnel fallout, die yourself. Yes. Because 1,000 amps at 12 volts, we're talking 12 kilowatts. So that's enough power to run a house now being dumped into something the size of a brick.
Then how does that mean that it's charging a battery from one car to the other?
Good question. Not well. That's why when you're jumping one car to another, you want to very carefully make the final connection away from the actual batteries onto just some part of the metal frame. Because when a car battery is dead, it is chemically very, very unhappy because it's got lots of lead sulfate. It's generating various gases of sulfates. It's putting off hydrogen gas, all sorts of just kind of stuff that very readily will ignite. And if you've ever jumped a car, you see that when you make that final connection, it'll make a fairly significant spark. That spark is because there is no current limiting when you hook up 2 batteries in parallel. And so it will very gladly, very quickly draw as much current as it can from the second car. Which is why usually you want the second car to already be running, because if it's not the fact that the battery was just dead and there's happened to be something else wrong with the electrical system, you can actually then have 2 cars that don't start. And one very mad neighbor. Yeah. So when you're jumping a car, make the final connection away from it so that A, you don't ignite the battery, and then you don't leave it on for very long, so you're dumping a lot of power into it for the minute it takes to then start the car, and then you disconnect. So this is why jumping a car is a fast event, and why you don't want to generally charge lots of batteries in parallel unless you really know what you're doing.
Is there a reason why jumper cables don't have any internal resistance to deal with that?
Because you're trying to start a car with it. And so since a starter battery is designed to have as low impedance as possible because you're trying to draw lots of power to start a car, the jumper cables are also designed to have very low impedance so that you can start a car through. I have actually jumpered a locomotive before. There's locomotive jumper cables that are absolutely enormous, and they're like 100 yards long, or 100 feet long, and you would literally park 2 locomotives next to each other, and you, from one battery box to the other battery box, probably the largest non-super high voltage spark I've ever seen. And 64 volts hertz hand to hand, so left pocket, back pocket, left hand, back pocket, because 64 volts hertz, especially when there's essentially no current limiting on it. Did that answer everyone's questions about jumping cars? The fact that it's becoming harder and harder to find actual metal frame now in cars is highly annoying for those of us who actually know why we want to avoid connecting to the battery, because I like my hair and skin and face. Plastics. So constant current stage is merely to limit the power. Is you don't want to deliver too much power to the battery merely because you will excessively heat the plates, possibly warping the plates. You will boil off, like thermally boil off the electrolyte inside of it, which is A, bad because you're losing your water, and B, bad because you're boiling sulfuric acid, which is bad, right? Raise your hand if you think it's a bad idea. Thanks, I got a little more than 50% there. And so that's bad. So you have this constant current stage merely to limit power until finally you get to the constant voltage stage. 14.2 volts is one of the multitude of numbers you can see for a charging voltage, anywhere between 13.2 volts and 15 volts, depending on A, exactly which battery you're dealing with, B, what sort of charge you're doing, and C, what forum you read in. There's a tremendous amount of misinformation on batteries in addition to almost everything else you find on the internet. The reason why it's something higher than 12.6 is because at 12.6 volts, you have now matched the electrochemical potential of these cells, and it will do nothing. It will say, okay, cool. So, these cells want to be at 2.1 volts. They're now at 2.1 volts, and they don't really have that much motivation to convert the other 95% of the lead sulfate in them back into lead and lead dioxide. So you want to apply a slightly higher voltage to speed up this chemical reaction, this electrochemical reaction going on, converting the plates back into lead and lead dioxide. Conversely, you don't want to apply too high of a voltage. Have you guys ever done the little experiment where you take the 2 copper wires and you put them in a glass of salt water and you put them onto a battery and you see like gas bubbles forming on the copper wires, right? Fun trick. That is you electrically cracking apart water into hydrogen gas and oxygen gas. When you have applied more than, when you apply more than about 2.4 volts in a sulfuric acid environment, such as a lead acid battery, you will have gas, which is bad because you're A, creating very explosive gases, and B, you're losing water. Conversely, this is why we like flooded acid batteries, because we can just replace that water. So that's why I have to maintain my batteries, but that's why I can maintain my batteries. If we were using something else like the electrolytes that plants crave, it'd be a little bit harder to replace this electrolyte as it is broken apart. And then the floating voltage is a little bit lower than that because you don't want to run the risk of outgassing, but at the same time you want to compensate for what's called internal discharge. If you take nickel batteries are about the most noticeable for this. If you take a nickel metal hydride battery cell, put it on a table fully charged, and you come back 3 months later, it'll be flat. That's because just internally to the battery, it leaks power, right? Every rechargeable battery does. This is one of the big significant differences between a primary and a secondary battery. Secondary batteries tend to do this faster. By applying 13.8 volts, you can counteract this self-discharge and let it just sit there indefinitely without having to worry about it being dead the next time that disaster strikes. And again, you can find a dozen different voltages for any one of these that I quote you, except for probably 12.6. So there are as many answers as there are people. Is there any questions on that? Cool. I'm going to draw for you that charge cycle in a conveniently diagrammic form. So, our situation we have here is we have a dead lead acid battery, and we have some magical box that's getting power from somewhere else, and that we're applying voltage to this dead battery to recharge it. We're going to do 2 plots. One of them being the voltage of the battery, and one of them being the current that we're feeding into the battery over time. The initial state we're going to say is at 11.5. So this is 11.5. Obviously, this scale is broken because we're going to fully charge it up to the top of the scale. At first, the battery is going to want to draw as much current as it can, and so we're going to have a constant current stage. During this stage, the battery voltage will slowly go up to whatever we determined to be our final charging voltage, which in this case I'll say 14.2. Once it finally reaches this full state of charge voltage, it's not actually done yet. We've done probably 80–90% of the actual work, but lead acid is a very slow chemistry of battery, in that if you fully discharge a battery very quickly and then disconnect it and let it sit there, you'll see most of that voltage come back. Because, as you saw in this equal diagram over here, in the short term, the only electrically available portion of the paste is the stuff right on the surface. If you then fully discharge the surface paste and disconnect it and put it over there in the corner to deeply contemplate the implications of life, all of the center paste that's not discharged yet will recharge the surface, right? So it's a very slow chemistry. Conversely, when we have the outer sections of these plates fully charged, the inner plates aren't yet fully charged. They'll partially charged. But from this point to this point, we will see the current slowly drop off until at some point we say, all right, we're at our full state of charge, and the current draw has gone from 10 amps down to half an amp, 100 milliamps, 10 milliamps, 10 microamps. Depends exactly how big your battery is. My big battery bank, I charge it at 10 amps. If I were to try and charge this adorable little battery at 10 amps, it would not work out so well. So your exact battery current will be based on the size of the battery and its capacity and how quickly you need it charged. So for example, Nolan charges his car much faster than I charge my emergency battery bank because my emergency battery bank has several months to years to charge, while he wants his car fully charged tomorrow at 7 a.m., 10 a.m., 11 a.m., college student, so 2 o'clock in the afternoon. At this point, though, we're going to say, hey, at this point, we're now fully charged. So constant current, constant voltage, and at this point, we're going to say we're fully charged, but we want to keep this battery charged indefinitely, and thus we go from the charging voltage to the floating voltage. And I'm running over time, I apologize. So at that point, you just drop the voltage down to something a little bit less aggressive, like 13.8 volts. Is there any questions on that? That's pretty much what I just said, but now I'm diagram form. Cool. Now we're going to talk about this magical box here about lead-acid battery chargers. When you design a lead-acid battery charger, you have to look at your specific scenario. What battery am I charging? What source of power am I using? How quickly do I want to charge this battery? Et cetera, et cetera, et cetera. That will dictate exactly how big you make your charger and exactly what parts of these curves you focus on. If you're looking for something that you can take your radio, drop it on it, and come back 20 minutes later and it's going to be mostly charged, you would really only be interested in the constant current part. You wouldn't be so interested in really ensuring that you get this termination perfect, because if you're dropping a device onto it, coming back 20 minutes later and taking it again, you're never going to reach this point. Conversely, on my emergency backup system, I'm mostly interested in this charge termination region because this line goes out for several years, right? And so after an emergency, I'm only going to actually be charging my batteries for maybe a day, and then it's going to hang out in this region. So when you design a battery charger, which you can now do because I'm giving you free batteries, although you could do that anytime you wanted, you want to decide about what you care about here. For the SLAs like this, what you're most concerned about is going to be is the charge termination state, because if you just have a sealed lead-acid battery hooked up, that's what you're going to be most interested in. You can also choose to only implement certain portions of this curve. So for example, I have recently built myself a very adorable battery charger here. At this point, it is 8 o'clock, so if anyone needs to leave at this point, feel free to, please. Yeah, no problem. Yeah, sorry. So this battery charger is a 1 amp constant current battery charger that, once it reaches the target voltage, terminates and disconnects the battery from it. Right? So this battery charger only does the first third of the curve. Right? It doesn't do any constant voltage mode, and it doesn't do any floating mode. And the only way that it starts recharging the battery is if A, you push the button on the side of it, or B, the battery gets to a discharge state of below 12 volts. Right?
Now, what do you use that for?
What do I use this for? charging my CL acid batteries I have. Right. What I have a solar panel, a little 10-watt solar panel that plugs into this, and so at field day source of operations, that's kind of a little gimmick. I set up the solar panel and say, look, we could survive off the grid indefinitely. Right. How I actually usually use it to charge my SLAs is I use a laptop power supply to plug this into the wall, and then I charge my SLAs off of wall current, which actually charges my batteries in a reasonable amount of time because sunlight. Conversely, I have to make sure that this battery charger limits current, because with a 20-volt laptop power supply, you put 20 volts onto a battery like this from a laptop power supply, it'll freaking dump power into there until either your battery explodes, your wires melt, or your laptop battery supply dies, as Jeff McGovern just realized last week.
So which one happened?
He killed the wall wart. Yeah, we're sad. Particularly because it was my wall wart. Conversely, if we know that whatever power source we're using has a low power potential, so like say a miniature little wind turbine, a 10-watt solar panel, and we know that 10 watts dumped into our battery at in any case isn't going to do any serious damage to it, we can essentially ignore the constant current section and just do constant voltage. Right. 20-volt solar panel, we regulate it down to 12, to 13.8 volts, and we just apply voltage to this battery. And if it tries to draw more current than our solar panel can deliver, the voltage goes down, because solar panels aren't infinite sources of power. Does that make sense? You could conversely just do a charge termination trickle charger, and it would take forever to charge the batteries initially, but it'd be a really simple battery charger, and is no credit, by the way, because it's just a voltage regulator. Right? So we now need to design circuits to A, limit our power, and B, control it and somehow terminate the charge. So for this assignment to get a free SLA, you need to have some sort of intelligence in this battery charger so that it will at some point switch from one mode to another. Mine switched from constant current mode to off. So here's the controller. The controller is going to be relatively simple from an electronics standpoint, because you're going to take, and this goes to the battery. The controller is going to be relatively simple because you're just going to need to look at the battery voltage and compare it to some reference voltage. How I did it in this was that I used a stable 5-volt voltage regulator as a voltage reference. So I put in 12 volts here, ground, and then out of the side of here, I put in 5.0 volts. And then I compared this 5.0 volts to a voltage divider with 2 resistors of the battery voltage. So again, here's the battery voltage here. And then this point right here, I designed so that at the correct point of stage of battery full chargedness, it would compare to this 5 volts or some fraction of 5 volts appropriately. Right, so at some point this is going to say, oh, this battery voltage, some fraction of it has gone above 5 volts. At that point, this trips a latch, which is a set reset latch. I don't remember how to draw that. I have a latch, an electronic latch in there, so that when it reaches the full state of charge, it then sets this latch and disconnects the charger. The reason that we have to have it be a latch is because as soon as you disconnect 14.2 volts from a battery, it's going to start drifting back down to 12.6 volts. I then have a second comparator to compare this fraction to the state of discharge, which is 11.7 volts, to set the latch, right? So we have this, all the circuitry again, is that I could do this all with discrete 7400 logic. There is 7400 logic for a set reset latch. There is analog components for comparators, 311, element 311, that comes to mind. But two comparators and a set reset latch are all conveniently included in a 555 timer, which many of you in electronics have used because the 555 timer is about the most classic IC there is. If you look internally to it, which can be done by either pulling up the data sheet or just looking at my t-shirt on some days, it has inside of it 2 voltage references, 2 comparators, going to a set reset. This is a good way to do your controller. Right? Have 2 voltage dividers coming down, one of them set to 2/3 of 5 volts, and one of them set to 1/3 of 5 volts for your high and low points, and then really read the data sheet for the 555 and figure out which one of those 2 will trip the output going high and which one will trip the output going low, and then you can have this go to control your power limiter. Right? Does that make sense? I'm so sorry I've been going all the time. I promise I'd keep it an hour right there. All right. So now we want to do our limiter. This is where we get to that nebulous analog magic stuff that, thanks to it in the 21st century, is all solved by the fact that we have increasingly more specific analog components to solve problems for us. A constant voltage regulator is not particularly interesting. You merely have a voltage reference of some sort of diode, and then an amplifier and a power amplifier in front of your amplifier. And you have this control loop, and if you just search for voltage regulator, you'll get more literature on it than I could ever write. Constant current, on the other hand, is a little bit more difficult because most people say, I want 5 volts, not I want half an amp. One solution to the constant current problem is using mess this up. A PNP transistor. So here's a transistor. This goes to our battery. Here we have a resistor, and then whatever our power source is. Solar panels, laptop wall wart, wind turbine, Nolan on a bicycle, whatever you want. This is called a current sense resistor. I say that because we're going to use this resistor to sense current and use that to limit the current. Current sense resistors are typically in the sub 10 ohm range. I personally, for projects, use 1.5 ohm resistors that are rated for 1 watt, and I have a 1/4 ohm resistors that are rated for 5 watts. If you figure out how much a 1/4 ohm resistor rated for 5 watts can pass, it's something significant. If you look in here, the current sense resistors are right next to the blue switch and are the 2 unusually large resistors that are larger than your typical 1/4 watt resistors you've ever seen. So PNP transistor, and then to deliver current into the battery, we need to pull this gate. We need to pull current out of this gate, because with PNP, small current here causes big current here. So we need to pull a little bit of current out here at just the right rate to make sure that we never exceed whatever our current limit is. To do this, just like with the voltage regulator, we use diodes as a voltage reference. So from our power supply again, we have 1 diode, 2 diodes, down to here, and then a resistor in the like 1 k ohm to 10 k ohm range, down to our controller. So here's our controller, right? And so when the controller wants us to deliver current, it will pull this low. When it no longer wants to deliver current, it will let this float. Right? What the heck is going on here? What I've done is I've used two diodes in series as a 1.4 volt reference. Right? Each one is 0.7 volts forward, kind of, usually. So between here and here is 1.4 volts.
So whatever you're putting in, it's going to be dropping by 1.4 volts.
Exactly. So if we have 20 volts in, we're going to have 20 minus 1.4 plus 18.6 volts, right? Here. Right? We use silicon diodes because silicon diodes are very not so interested in exactly how much current you put through them. They will usually tend to be very close to this 0.7 volts. Right? Conversely, this PN junction right here is also a 0.7 volt silicon junction. And so while this point right here at the base of the transistor, we know this is 18.6 volts, this point right here, the emitter of the PNP is 0.7 volts more than that, which is going to be 19.3 volts. So we know that the top of this PNP transistor is 19.3 volts, and we know that the top of this is 20 volts. So I mean, really what we've done here is we've ensured that whatever this current sense resistor is, we always have 0.7 volts across it from the top diode. Yes, sir?
The PMP also drops the fixed voltage?
Yes. Because the PNP is one silicon junction from the P up here to the N here, which is exactly the same as the P to N inside the diode and the P to N inside the diode. The P to P section of the transistor here that most of the current is passing through doesn't have any definite lower limit on its voltage. So we know that it's 19.3 here, we know it's 20 here. Hey, using Ohm's law, we can now calculate how much current is going to pass this resistor because we've guaranteed that this resistor is always going to have a certain voltage across it, right? Current equals voltage divided by resistance. So we have a 1.5, just let me easier than that, 1.4 ohm resistor, 0.7 volts over 1.4 ohm resistor. We know this is going to be a 0.50 amp source. If we try and draw more power from this circuit than that, so we try and draw more than half an amp from the circuit, it'll pull this point lower, right? As we try and pull current, the voltage here will drop because the voltage across this resistor will be above 0.7 volts. If this point right here is below 19.3 volts, and since the base here is fixed at 18.6 volts, we'll no longer have 0.7 volts here. If we don't have 0.7 volts here, we can't get the tiny current here to drive the big current, and the transistor will turn off. Right? And so even though we have a 11.5 volt battery here that's trying to draw a couple kilowatts, it's only going to be allowed to draw 0.5 amps at 11.5 volts, and suddenly we're missing a bunch of volts because the top of this is 11.5 volts, the top of this is 19.3 volts. The difference between those are inside the transistor, and the transistor will very quickly get very hot. Have I blown all of your minds thoroughly on the concept of a constant current source? Mind blown. You have to be real careful you don't blow up this transistor. Conveniently, there are special transistors that are specifically designed not to blow up. Here is one of them. Thanks to Adobe for scanning and talking. The LM317 3-terminal positive adjustable regulator. It's not a transistor, is it? It's a freaking voltage regulator. We're doing voltage-driven current. The difference between current regulator and voltage regulator is that we're regulating the voltage across a resistor to cause current later. So just as you can have a actual discrete transistor and you have 0.7 volts across here because the diode, blah, 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 you can use an adjustable voltage regulator which guarantees that between its output pin and its adjust pin, you always have 1.25 volts. So you want to read the LM317 data sheet to understand that statement I just gave you later, because I'm running out of time. 317 voltage regulator, input voltage 20 volts here. Adjust pin here. And out here. The LM317 guarantees that it will do everything it can to keep this output voltage at the adjust voltage plus 1.25 volts. So if we use that property of this to our advantage, we can have a current sense resistor from this output back to the adjust pin and then to our load. So 317, output pin, current sense resistor, feedback, or sampling, I guess, to the adjust pin. So if in the example of this, we have a 1.5 ohm current sense resistor here. Since this point here is held 1.25 volts less than here, we know that 1.25 volts across a 1.5 ohm resistor, hey, that's like 0.8 amps, right? So this device is always going to deliver 0.8 amps. Down here, I've placed a something in the range of 1 to 10 kilo ohm resistor on this feedback here, because now we can shut down this regulator by just pulling the adjust pin low. That didn't make any sense. I'm sorry that I explained that poorly. We want to be able to turn this current source off later. If we didn't have this resistor here and we just had this and this, we wouldn't have any way to do that, because the 317 does everything it can to keep this point 1.25 volts above this point. So what we do is we put a large resistor here that doesn't have any current drop, doesn't have any voltage drop across it. So under normal conditions, this point and this point are the same voltage. But once we realize that the charge is done, we can using a transistor or a relay or a switch or something, ground this point. 317 will very carefully always keep this point at 1.25 volts above ground. And then as long as we make sure that the battery won't then come back and blow up our regulator, it'll stop charging the battery. This is what I do. If you wanted to instead have it actually start slowing down this current source and keep it at 14.2 volts until this voltage here gets smaller than some fixed amount for some low-end current, and then say, now my battery's done, so if you want to have it be smart enough to do the last 10%, that would just be one more op amp than I was willing to use in a Alto's tin. Right? So this turns it on and off. Then at this point, we now have just a big, hefty diode to keep the battery from feeding back into us. And then right here, right where the battery connects to it, I have this circuitry sampling the battery voltage, checking it against my battery reference, and then this is just a 1 k ohm resistor, standard signal NPN transistor, going to ground. And this point right here is this point right here. So when the battery voltage reaches 14.2 volts, this set reset latch sets, through this 1 k ohm resistor, it turns this transistor on. And this is your standard 2N3904 standard NPN signal transistor, because you're only passing like 1 or 2 milliamps through this transistor, because that's all you need to control a LM317. Ground's the top of this, so this goes low. Since this goes low, because you're imagining these 2 points are connected together. I'm sorry, this isn't like a torus chalkboard. When this goes low, this point is held at 1.25 volts, which is less than the battery voltage. This diode doesn't conduct backwards, and the battery charger and the battery are now essentially disconnected from each other, except for this sense resistor right here. This resistor, plus in practicality, how I have it is I actually have a variable resistor in the middle. Those 3 resistors are up in the 50 k ohm to a mega ohm range. So we're drawing maybe a milliamp total. I actually have 2 LEDs on there, just little indicator lamps. They draw more power than that. Right. The reason I used 3 resistors, one fixed, and then an adjustable in the middle, is because precision resistors are expensive. You know, a 1% resistor is 10 times as expensive as a 5% resistor. Getting the exact resistor values I needed to get 12.6 volts divided down to 3.66 volts is really kind of inconvenient. So I just picked something here that was ballpark about what I needed, something here that was ballpark about what I needed, and if you look in the battery charger, there's 2 little dials in there that I turn with a screwdriver, and so I set this voltage point, this voltage trip point, exactly where I want it. So that is a battery charger. Obviously, I didn't put it all back together as one beautiful schematic because A, I want to leave this a little bit more open-ended than that, so that you guys can kind of come up with what you want to accomplish with your battery charger. Feel free to please come and drill me for questions anytime you want to, and I'm available because it's my job to help you guys build this sort of stuff. And I will be documenting my design on my website, which you guys so fastidiously wrote down at the beginning of the lecture, blog.electricalf.com. So I'll try and put that up at some point next week. And that's how you charge a battery. Question?
All the components that you mentioned in the last half hour are stuck in the check?
Conveniently, yes. Well, we do not stock 317s. We stock 1117s. Better version of this, in that the 317 must have a supply at least 2 volts higher than the load. 1117s only need 0.7 volts. So we can charge batteries from 15 volt supplies instead of 17 volt supplies.
Any other questions? All right, well, thanks, Shannon, for putting together the presentation.
Thanks for having me.